An isolated transformer is defined as a transformer that has no electrical connection between its primary and secondary windings, meaning the primary and secondary circuits are completely isolated. A separately derived system is defined as an electrical system that is not directly connected to the grounding electrode system of another system. This implies that the separately derived system must have its own independent grounding electrode system. In a typical residential scenario, a house is generally not considered a separately derived system because it is connected to the power company's grounding electrode system. Even though the transformer on the power pole supplying power to the house is an isolated transformer, it remains connected to the grounding electrode system maintained by the power company. Therefore, the house does not qualify as a separately derived system. To further clarify, let's delve into the specifics of grounding and bonding in electrical systems. Grounding refers to intentionally creating a low impedance path to the earth, enabling the stabilization of voltage to earth during normal operation and limiting the voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines. Bonding, on the other hand, involves connecting metallic parts to form an electrically conductive path that ensures electrical continuity in the capacity to safely conduct any fault current likely to be imposed. A grounding electrode system typically includes items such as a ground rod, ground ring, or metal underground water pipe. This system is essential for providing a path for fault current to return to the source, which facilitates the operation of overcurrent protective devices like circuit breakers or fuses, clearing the fault quickly and safely. The purpose of a separately derived system having its own grounding electrode system is to ensure that any fault within that system is safely cleared without relying on the grounding system of another electrical source. Considering a separately derived system such as a generator or an on-site transformer providing power to a specific load, it must have its own grounding electrode system that is independent of the utility's grounding system. This independent grounding system is crucial for several reasons. Firstly, it limits the ground fault current to a level that can be safely handled by the equipment within the separately derived system. Secondly, it prevents unwanted ground loops that could cause noise or interference in sensitive electronic equipment. Thirdly, it ensures that the overcurrent protection devices within the separately derived system operate correctly in the event of a fault. The NEC, or National Electrical Code, provides detailed guidelines for the installation and grounding of separately derived systems. NEC Section 250.30 specifically addresses the grounding requirements for separately derived alternating current systems. This section outlines the necessary steps for establishing a proper grounding electrode system, including the sizing of grounding electrode conductors, the selection of appropriate grounding electrodes, and the bonding of metallic components. For example, NEC Section 250.30 outlines the general requirements for grounding separately derived alternating current systems. It specifies that the system must be grounded at the source, which is typically the transformer or generator. The grounding electrode conductor must be connected to the system's grounded conductor, and the grounding electrode itself must meet the requirements of NEC Section 250.52. NEC Section 250.30 provides specific rules for the size of the grounding electrode conductor. The size of the grounding electrode conductor is based on the size of the ungrounded conductors of the separately derived system. Table 250.66 in the NEC provides guidance on selecting the appropriate size of the grounding electrode conductor based on the size of the ungrounded conductors. NEC Section 250.104 addresses bonding of piping systems and exposed structural steel. For a separately derived system, it's crucial to bond metallic water piping systems and structural steel that are likely to become energized. This bonding ensures that any fault current will have a low impedance path back to the source, facilitating the operation of overcurrent protective devices. In contrast, in a typical residential setting, the utility transformer is grounded at the transformer location, and this ground is extended to the service entrance of the house. The neutral conductor is bonded to the grounding electrode conductor at the service entrance, creating a single point where the grounded conductor is connected to earth. This arrangement does not qualify the house as a separately derived system because it relies on the utility's grounding system. Let's consider a practical example of a separately derived system. Suppose a building has a large solar panel array with an inverter that converts direct current, DC, from the solar panels into alternating current, AC, for use in the building. If the inverter is designed to operate as a separately derived system, it must have its own grounding electrode system. This means that the inverter's neutral conductor must be bonded to a grounding electrode conductor, which is connected to a grounding electrode such as a ground rod or a ground ring. This ensures that any fault within the solar power system is safely cleared without relying on a building's main grounding system. Another example might involve an emergency generator installed to provide backup power to a critical facility like a hospital or a data center. In this case, the generator is typically configured as a separately derived system. When the normal utility power fails, the generator starts up and its output is switched to the building's electrical system through an automatic transfer switch. The generator must have its own grounding electrode system to ensure that it can safely handle any fault current without relying on the utility's grounding system. It's essential to understand the distinction between separately derived systems and other types of electrical systems to ensure that electrical installations are safe and compliant with the NEC. Incorrect grounding can lead to dangerous situations such as electrical shock, fire, and equipment damage. In summary, a separately derived system is an electrical system that is not connected to the grounding electrode system of another system and has its own independent grounding system. Your house, powered by a transformer on a power pole, is not a separately derived system because it is connected to the power company's grounding electrode system. The transformer on the power pole is an isolated transformer, but it is still connected to the grounding electrode system of the power company. Understanding these concepts is crucial for ensuring the safety and proper functioning of electrical systems. When in doubt, it is always best to consult with a qualified electrician or electrical engineer to ensure that electrical installations are performed correctly and in accordance with all applicable codes and standards. The consequences of improper grounding and bonding can be severe, so it is important to take these issues seriously. Understanding the concepts of isolated transformers, grounding electrode systems, and the requirements outlined in the NEC are essential for ensuring electrical safety and preventing potential hazards. Always consult with qualified professionals for electrical work to guarantee safety and compliance.